diffusivity to be as small as possible, which is a very dangerous thing to do. And the hash set of simulation, now it's explicit dissipation. It's a constant classical way of doing things, if you want. And so you just have a fixed value for all your diffusivity, so you can fix your parameter, your a-dimensional parameters if you want. Now, this can look like a very bad idea, but you can still work with that in some sense, and you can try to make sense out of it. So I just want to mention that we are close to reaching convergence in this code for non-rotating hydro cases. That is shown with the work we did with my colleague Gustavo Guerrero. It's a paper that is on arXiv and should be soon published. When you see here, when you increase the resolution of the numerical simulation, your spectra actually start to converge at some point when you're not non-rotating and non-magnetic. So at least in that regime, you can access something that makes sense and makes sense out of your simulations. In the non-rotating case, it's still not the case, and in the MHD case, it's not the case as well. That being said, once you have a simulation run like that, you can estimate what is the effective dissipation you have in your model, right? You can try to assess what would be the equivalent Reynolds number, what would be the equivalent Prandtl number in your simulation. And to do that, you can design a spectral scale-by-scale force balance budget or energy budget if you want, and just compute in this regime, well, what is the missing term? What is the numerics? What are numerics doing? That's the game we played back in 2016, and we played it again in this paper. And we were able to actually, well, put some numbers or some estimate of what is the effective Prandtl number. It's not perfect, because of course, with this kind of scheme, you can have a very different Prandtl number at different location on your sphere, for instance, depending on how turbulence develops. But it gives you a rough idea on average of what are the turbulent properties of your model. And in that paper, when we did that game, we actually put back these values that we got into an explicit code, and we are able to match the two codes quite satisfyingly. So you can make sense. You must be very careful about what you say out of this simulation, but at least you can make some sense out of them. Okay. So I want to touch on 3 topics today. What it sets in this simulation, the differential rotation, which is a key ingredient for dynamo, as we've heard, at least stellar and solar dynamo. What is the origin of magnetic cycles in some of these simulations? And what can we say about the energy budget of these simulations as well? Okay. So we've seen that before a lot. The differential rotation of the sun, fast equator, slow poles, a strong shear at the Takehome line, some shear at the near surface, and conical contours here, so not very strongly constrained by rotation and mid-latitude here. So when you do I'm showing you here a parametric scam in one of these 2 studies. This is with the hash code. So we are varying rotation rate of the model here, and what we would call the mass of the equivalent star. So it's the depth of the convective envelope, basically. And so you're changing your Rossby number and your convection scales as you move from left to right. And so what you see here is that we have a clear trend in that when you're in the upper right part of the diagram, you have what we call the anti-solar differential rotation. So you have a slow equator and a fast pole. When you're in this middle diagonal here, you look kind of like the sun, basically. Fast equator, slow pole with conical contours at mid-latitude. And when you're in this lower left part of the diagram, you have banded structure for the differential rotation, which is a Taylor-Palmer constraint that you just witnessed here. Okay. When you run these exact same cases with magnetism now, well, basically it's almost the same picture, except that here, well, the boundaries between these regimes just vary a bit, but here you have just completely erased those banded structure because you have strong magnetic field that is generated that just erased, well, the shear basically, and you just decrease by a lot the differential rotation you get in these fastly rotating models. So this is not all new, of course. This was, for one of these transitions, it was very nicely illustrated by this paper by Thomas Agustin in 2014, where you have at a given Rossby number a transition between positive differential rotation and negative differential rotation, which would be, so in our case, solar-like or anti-solar-like, okay? And so if you plot it in an astrophysical way, if you want, in terms of observables, or almost observables, if you wish, so mass of a star versus a rotation rate, you get such kind of transition when you would get from anti-solar to solar to banded or no differential rotation or very weak differential rotation because of magnetic feedback, okay? So now you can play the game of trying to see, well, where is the energy sustaining all this differential rotation coming from in this simulation. So you have different reservoirs to play that game. And the one would be interested here in is the differential rotation in red. So it can be affected by Reynolds stresses directly from the well, sorry, this will be internal and potential and fluctuating energies. Sorry, because you have some kinetic energy as well. So Reynolds stresses can sustain your differential rotation. You can exchange some energy with a meridional flow, and you can have also the Lorentz force feedback in image D. So when you play that game and you plot in this series of simulation as a function of Raspbian numbers, this is the kind of budget we get. So this is a bar plot divided by the luminosity of the star, so the amount of energy that is transmitted throughout our convection shell, basically, okay? So you get a transfer of energy divided by that, the power, if you want. And the yellow bars here correspond to the Reynolds stresses, the transport of energy. The magenta part, which is the big one here, is the viscosity we have in our model. And the red part is the feedback from the magnetic field, so the Maxwell stresses here, okay? And so you see that as a function of Raspbian number, we have clear trends. Globally, all our differential rotation in this model are sustained through Reynolds stresses, basically. You have at high Raspbian number, it's equilibrated by the explicit viscosity we have, which can be seen as a turbulent viscosity if you want. And for the fast rotating case, you see that the feedback from the magnetic field is actually very strong and playing the main role here in the equilibrium, which is why you actually suppress your shear. And in these cases, you have almost no shear left in your differential rotation, okay? And you see that you have a sweet spot at intermediate Raspbian number here, where you have the maximum power involved into your sustaining your differential rotation in this model. This is globally on the full convection zone. And what I want to convey here is that actually to look at the actual number, this is very big, if you want, because the power that is involved in sustaining differential rotation in our models reach up to 30% of the stellar luminosity. So this is a very large amount of energy that is, of power, sorry, that is involved in sustaining that. Okay, now next, the title of the course was cycles. So let me talk about cycles in these models. What do we find? So we find also something that is coherent between those two sets of simulations, and I will use figures from both sets to illustrate that. Is that when you have a small Raspbian number, typically you can find two types of magnetic cycles, okay? In these simulations. You can find a deeply seated convection cycle that is typically, if we rescale things, well, if we calculate in physical units, it's order of a year, tens of years, sorry, a decadal time scale. And if we just remove this signal at the surface, so this is a zoom on that, but at the surface of the domain, you see that we have also very short cycles that start to appear. And these very short cycles are yearly or even less than that, and we see a very distinct pattern in these fast rotating cases. When you're in intermediate Raspbian number, we completely lose this behavior in those models, and we find again the decadal cycle dynamo. And then if you increase again and you go into the antisolar differential rotation regime, we completely lose in all models the cycle, and we just get a stable west, which still have some significant amount of magnetic energy, but it's not reversing anymore. So just on a side note, some of these models exhibit very interesting behavior in terms of family of dynamo family we get out of those models. They can get sometimes dipolar, sometimes quadrupolar, and vary in between those two families. Some of them just stay in the quadrupolar family, some of them stay in the dipolar family, and some just, like this one, just switch from one to the other depending on the epoch of the simulation. Of course, we cannot run them for such a long time, so this is already very difficult to run them for this kind of time scales. So if I just try to summarize that, so this is a plot of the differential rotation kinetic energy over the total kinetic energy as a function, again, of the fluid Raspbian number. What we find within these two sets of simulation is that, again, for very low Raspbian number, well, not very low Raspbian number, let's put it this way, we have short cycles that are seated at the top of the convection zone near the equator. In the middle, we have models that have decadal cycles that are deeply seated. The bulk of the magnetic energy is actually at the base of the convection zone of those models, and they invert on a decadal time scale. And then if you push the Raspbian number higher, you just completely lose the cycle, but you still have a significant amount of magnetic energy. And what I want to say here is that the Raspbian number regime, where we actually find those decadal cycles, is actually quite small. as you can see here. And I think that's part of the reason why in the past, many attempts that tried to actually recover this cycle were not successful, because they actually exist in these simulations and in this parallel regime over a quite narrow range of Raspberry number. Now that gives you some, as I a bit conveyed before, that gives you some caution when you interpret that, because you say, well, now if these stars, or if this model has some relation to stars, and actually you can have very different cycles treated differently at different locations and not necessarily associated with an inversion, well, maybe you should not compare all this, right? How do you know which one is actually the same as the sun, where you have a nicely correlated activity tracer with the long-term cycle, and all these guys actually have anything to do with the 11-year solar cycle. So that's just a word of caution here. Now, let me go a bit deeper into how we understand this cycle to work in this simulation. This is a plot for two reversals of different energies, and I just want you to focus on the magnetic energy, which is in red here, and the differential rotation energy, which is in green. This is only the energy within the convective envelope. And what you see here is that you have a perfect anticorrelation between the two. This is a log scale, and actually all the energy that is getting up and down here is actually this one that's getting up and down here. So you have a transfer of reservoir of energy for the cycle. This is the cycle you see here, from the differential rotation to the magnetic energy here that is in not in equipartition. This is below. So if you try to take a closer look, you can look at this variation in the differential rotation, which is, so I've just averaged the differential rotation over time, and I take the instantaneous differential rotation minus this average one and divided by, again, the average over time. So it's a relative variation of the differential rotation, or the torsional oscillation, as we call them in the sun, if you want, as a function of latitude and time at the bottom of the convection zone of one of these models. So you see these alternating red and blue patterns that are, well, this variation of the differential rotation. And if I overplot the azimuthal mean azimuthal field at this depth, you see that you have a perfect correlation between the two. And if I go even further and I try to actually estimate this mean field term, that is the shear, the omega effect, if you want, so the shear of the polyidal field by the differential rotation, you see that it's actually reversing b phi each time, well, exactly at the same location. So it is what we find. So it's not shown here because that will be one too many contours, and it's already a lot of contours on this plot, I'm sorry. But the polyidal field actually reverses right after this transition in b phi. So it's actually this variation of omega, or u phi, that actually trigger the cycle, at least in these simulations. So it's interesting because it's a kind of a new way of actually driving a cycle, if you want. Not so new, it's been explored in some models, but it's not a widespread way of doing that. So now if you're looking again at this cycle period of a rotation period, now as a function of Rossby number, so this is the data set in stars with oil lag. This is a data set with ash. We see some convergence of the results. But this year, Petri Kapila compiled an even larger sample with other codes that find also some cycles, and it starts to be a mess, right? So we have these results with the OLAG code are in blue. Then we have some results from Jornbadeker in red that were kind of agreeing, or at least the same kind of trend we were finding with the pencil code. Then Petri with the pencil code has new results which are in black here, which are quite flat in this diagram. And Gustavo Guerrero in 2019 actually published a series of models that are actually going the other way around. So we do have in all these models, even some of them use the same code, we have some significant difference in the trend we observe in this cycle. And this is very problematic in many sense because each of these simulations is actually very costly. And so we can not do as many parametric explorations. So we really need to understand what's going on here and what is actually related to dynamo cycles in stars. Some of the differences certainly arise from a difference in force balance, or if you want, for differences in Pareto regime. But clearly, some of them actually rely on how the two boundaries of your convecting shell are treated. And in particular, in this recent paper from Petri, he involved an outer boundary that is a bit more realistic than what people typically do. And that is certainly participating in changing how the dynamo is occurring within the convection cells. So that needs to be explored a lot more and explained, all these differences, but that's a bit where we are, I would say, right now in this business. Now, if I come back to the anti-solar diffusion, anti-solar differential rotation, sorry, so that would be higher up here on the right. So all the models that do not find any cycle, most studies that try to address in 3D this regime do not find any cycle. And so we've been, sorry, I'm just messing up my slides. Yes, okay. So we've been exploring that with mean-field models with Quentin Noraz in a paper that was published this year. And actually, we have some explanation as to why it's very difficult to actually get a cycle when you have a reversed differential rotation. So this is a classical picture. This is adapted from a Sanchez paper from Sanchez. So where we have the solar differential rotation that shears the poloidal field, you just get an azimuthal field like that is sheared. And then depending on how you restore your poloidal field, either through a Babcock-Clayton effect or through an alpha effect, well, both things will lead you here to a poloidal field that is reversed. So you cancel flux, you reverse it, and you have a natural way of actually driving a cycle in this way. Now, if you do exactly the same game, but you just reverse the differential rotation, so you shear it the other way around if you want, well, most of the paths that you will follow will lead to flux addition, and so you won't be able, from mean-field arguments, to actually easily explain why you would have a polarity reversal. If you play with the alpha effect and you localize it very close to the Takehome line and play smartly with signs, there are some good theoretical reasons for that, then you may have some cases where you can get flux consolidation, but for most of the case, you won't get a cycle, which is certainly why in the 3D simulation it's very hard to obtain the cycle when you rotate slowly and when you switch your differential rotation profile to be anti-solar. Now I'd like to finish with this last part, which is what is the energy budget of these turbulent simulations. So I've shown you the energy budget for the differential rotation. Now I'd like to do that same thing for magnetic energy. So when you're looking at reservoirs, magnetic energy, of course, is special because you have to go through flows to actually give energy to your magnetic reservoir. So as I said before, for the kinetic energy, you play around with potential and internal energy. And then you exchange energy through the Laurene force, basically, with the magnetic energy, and then you can lose some through ohmic heating, okay? Well, of course, this is a very simplistic way of looking at things, so let's get to the less simplistic way. So this is only for the mean field, okay? This is taken from a paper from Starr and Gilman in 1966, and we revisited this energy flow diagrams in our set of simulations. And you can actually address what exactly is sustaining your mean field toroidal, well, large-scale toroidal magnetic energy and large-scale poloidal magnetic energy, assessing all these different terms and seeing where the energy flows and how it's actually stored. Okay. So this is what we get for the toroidal magnetic energy. I won't show you all the balances. And it's a simplified world. We have aggregated some terms compared to the previous plot. And what you see here is that, as expected, the main thing that sustain your magnetic energy in this simulation is, of course, the omega effect. This is the blue bars here. And, well, due to a limitation of numerical simulation, of course, this is opposed by just dissipation. This is what Steve also conveyed in the beginning. When you in induction equation, you don't have much to work. You have the curl of U cross B, and then you have dissipation. So that's it. You also have a turbulence EMF here that can play some non-negligible role depending on the model. And that can also switch sign from one model to the other, which is, I think, an interesting aspect. And even to get a bit beyond that, you can also show this kind of plot as a function of time in one given simulation, right? That one that is reversing. So this is what I'm showing you here. You see how energy is transferred as a function of time in one of these simulations, okay? And you see that, so I have shown here in black the toroidal magnetic energy to show you well, basically one cycle. So you see you have a very big peak at the maximum of the cycle here, and the transfer gets really weak in between at the minima. And I think one very interesting result from this diagram is that the turbulent EMF switches sign in between the cycle, okay? So the turbulent EMF you get is actually mostly positive in the rising phase of the cycle, and then it's actually detrimental to the toroidal magnetic field in the declining phase here. So this is very interesting because you can see that from the same effect, you can have actually an incremental or detrimental effect to the total magnetic, well, here is the toroidal magnetic energy. Okay, so in a nutshell, if I want to summarize these results very fast, it's that for slow rotators, we involve a bit 0.01% of the solar luminosity to sustain magnetism in general, so this is for total magnetic energy. For a solar-like rotator, we're between 0.1 and 3. and it goes back to 1% for fast rotators. So you see that even for slow rotators, so the ones that are rotating with an anti-solar differential rotation, it's still a massive power. 0.01% of luminosity of a star is quite large. So you still have a lot of magnetic energy available to actually do whatever you want. If you want to flare, you can flare with that, for instance. So just to go fast, we've started to look at those simulations with Robert Cameron in a flex budget analysis. I don't have much time to cover that. But we can discuss that, and Robert will give you the primer on how you do that kind of budget, I think, tomorrow. And yes, to finish, before conclusions, we've heard from Victor some very strong constraints from demand Doppler imaging on stellar model dynamos, right? And so we wanted to check that. So when you look at the energy in this magnetic energy in this simulation as a function of Raspberry number, we find that we have roughly the energy that decreases linearly with the Raspberry number. So that would be that your average field within your simulation decreases like the square root, minus square root of Raspberry. But if you remember the plot from Victor, it's actually more like linear dependency. So we inquired into that, and actually we find that in those simulations, even if the total energy in the full convection zone scales like that, which is, well, what is expected typically from magnetosophy type scaling laws, well, if you look only at the surface field, it has a different scaling. And actually the surface field scales like Raspberry to the minus 1.3 in our simulation, which is quite close to the Zeeman Doppler imaging constraints. So it's interesting because as we are conducting everywhere in those simulations, well, the total magnetic energy content doesn't scale the same way with Raspberry number as a surface field that is the one that you observe. This is also a word of caution. When you take some observational constraint, you have to compare, of course, what's comparable. And yeah, that's a bit of a side note, but I won't enter details. So what are the take-home message? Okay, so those 3D model, the one I've been involved in and but also others, they can produce a variety of dynamo states right now. They can be steady, reversing, cyclic. They can do that with or without a tachocline, with or without a near-surface shear layer, and with or without spots, which says a lot about the robustness of actually doing cycles. Then doing exactly the solar cycle is a different story, of course. You can have very distinctively different types of magnetic cycles produced in those turbulent convection zones. And I think that's really important to realize when you compare to observational constraints, that you have to compare apples to apples, of course. Well, this is just, again, the numbers. And for the slowly rotating case, we have anti-solar differential rotations that have never been confirmed to exist observationally for main sequence stars. So that's something that would be very interesting to constraints or dynamo theory. They lose a magnetic cycle, and they maintain the strong dipolar component. And now I want to address problems, because I think it's important to be open with that. So conversions of the solution can be sometimes or often questioned in here, because we know we don't have this path, this clear path that Julien talked about yesterday, I think, still for stars. And so, of course, some of the results I've shown you are dependent on Reynolds, Prandtl, magnetic Prandtl, Ray number, and it's unclear how, well, what we should do still, I think, to my opinion. They may be reconciled with observed surface of the sun, because we are missing in most of these models a surface that is realistic. What is the exact role of boundaries? There are a lot of ideas, but no consensus in the community on that. Tachocline instability can play a role. Photosphere, chromosphere, corona coupling can play a role as well. And this is not fully understood, to my opinion. And then, of course, the elephant in the room, the convective conundrum, is still very much alive in all this study. And so we have several ideas I was mentioned in the past 2 days. And so we have to, well, have a consensus on that. Thank you very much.
Thank you, Antoine. Questions? Yes.
Thanks. I think that was a nice overview of kind of where we are with the global models. I have like a burning question that I ask all the global modelers, and since you're an expert, I'll ask you. In the plot by Gastine, the differential rotation actually seems to peak right at the anti-solar transition. And in fact, it's asymmetric, so the anti-solar states have the strongest differential rotation. And naively, I would expect there to basically be a spike in dynamo activity right at that transition, and I would expect that spike to be stronger for the anti-solar states. We clearly don't observe this. I guess my question is there any indication that that happens in the global models? Or if not, why is my thinking that the differential rotation should lead to increased dynamos at the anti-solar transition? I mean, why is that thinking incorrect?
So yeah, I think Well, there are a lot of parts in your question, to be honest, but I think there are some indication of that in some on the, indeed, that it's not fully clear. I mean, in the numerical simulation, at least in the energy budget, I've showed it's clear that right after that, in this regime, we have some kind of a sweet spot for dynamo action in the simulations. That is certainly associated with that. And then when you move to lower Rossby number, then you have still strong fields, but it's actually just suppressing the differential rotation, which is, well, what maybe you see here, and at some point, well, it's just disappear. Well, I don't, so here, maybe, Thomas, you can correct me. I don't remember how much of this are magnetic or not. But of course, it's also computed just for one latitude, I think, so that may also play a game when you get to a banded regime. So well, that's another story. In the observations, I think it's very hard to say actually confidently what occurs at this transition, because for real stars, and that's for many reasons. First is that for detecting rotation period of stars, most of the technique rely on the existence of spots. So you have modulation of spot as the star rotate, and that's how you detect a rotation period for a given star. Basically, that's the most well, you can do that with astereosismology, of course, but not for all targets. And so if you lose cycles, or maybe if you lose some spottiness aspect of your dynamo, well, it's just the star exists, but you don't detect them. So in the observation, it's unclear that actually those stars, you can plot them or have seen them in such a diagrams. Now, it's also possible that when you look at this thing, sorry, I'm getting back to the end. Should remove the animations. Yes, here, for instance. So this is just the dipole field at the surface of the model. It's indeed when you go to this transition, it rises up again, right? So, but we clearly have a minimum around here in this diagram, and it's unclear if stars could get stuck in here, actually, and so never enter this regime. It depends on the spin down lows you get, and so you may be aware of all the work that has been done in the past 5 years, let's put it this way. But maybe stars stop spinning down here because the spin down stops to be efficient it could be for many reasons. And if that's so, then they simply never enter that, and which is why observationally you cannot just detect them. That's one possibility.
So these dynamos with two different cycle periods are very interesting, and one of them relies on the interaction with differential rotation. So sometimes that's put forward as a mechanism for modulating the sun's.
Yes.
And the ratio of the periods depends on the magnetic Prandtl number. So I'm just wondering, what is the, I don't know, what's the effective magnetic Prandtl number of your simulation?
So we do find those models for both ILES and LES code. So these are the dual symbol here. So for these circles, they are with ash. So you have, well, the effective Prandtl number is slightly larger than 1 here. Okay. Magnetic Prandtl number, sorry. Yeah. We also find this dual state in the ILES for 2 cases here. It was a surprise that the deep cycle was actually, we think, moderated by this feedback, and it was just an added modulation. It's clear that for the short cycle, it's not the case. We do see some oscillations, but it's very weak. And so here we think it's more an alpha omega dynamo from quick analysis of a very simple way of estimating alpha in this simulation. So it seems to be 2 separated mechanisms making those 2, and actually they don't talk much to each other, but it's a very small sample. We have 4 points here, so it's hard to say confidently. Yeah. It's the case, yeah.
Okay, thank you.
Are there any other questions? Yes. Yeah. I'm coming.
So let me focus on the change of electromotive force sign. So that's very interesting for me, a turbulence researcher. So then I know you don't need to rely on any mean field theory, but still I'm very interested in if you check the temporal evolution of several mean field terms, including turbulent energy and helicity and also cross helicity. Yeah. Then what kind of behavior they show across polarity changes?
Yes. Okay. Yeah. So we have not tried to estimate it in detail, okay, to be honest. So we have just tried to estimate the alpha effects with just the helicity and current helicity. We've tried both. And we've just checked that on 2 models to see that it was robust. We have, I don't know here. This is the one that changes sign. It would be the equivalent alpha of an alpha square for B phi. That changes sign because it was for toroidal magnetic energy. Okay, so we have not seen a reversal of this equivalent term in the boloidal part of the dynamo action. So. But we could, I mean, we have all the data set and we could do a test field or whatever method if we have access to a code to do that. We could try to estimate that as a function of time, but it's not as well. We've not done that yet.
Okay, thank you.
It's just from an energy perspective, we see that, and that would be the equivalent effect, net effect in terms of energy budget of an alpha term, if you want. Yeah.
But still, I also interested in the other helicity.
Yeah, I understand that. Yeah.
So
Mm-hmm.
because it should change sign
Mm-hmm.
in time.
Again, it's, yeah, well, it could be also a very localized effect in terms of how the sign change because, yeah.
Okay, I think we need to move to the next speaker now. Thank you again, Antoine.